And okay, well, we'll get started. I'm sure we've got more people joining, but I want to make sure we got plenty of time because this looks really interesting. So, hey, Ted, thank you for coming. I'm very excited about seeing your take on test-driven development and also especially your game. That sounds like it's going to be a lot of fun. So I will and I discovered you were in California. I thought you were somewhere else. So if you can give us a brief introduction and then dive on in, and this is going to be fun.
Yeah, yeah, thanks, Mark. So my name is Ted M. Young, and I'm a software developer, trainer, coach. So I've been doing software development for, let's call it, several decades. So I've been through all the different things. Um, I currently do technical training focusing on test-driven development. And of course, as part of that, refactoring techniques, especially focused in Java, as well as coaching teams using mob programming and ensembling to help people get better at the skills that I think they need to learn, and that are often difficult to do in sort of realistic code bases. So I've been working for I worked for Google, I worked for eBay, I worked for Apple, I worked for smaller companies, and all of them had, similar issues with very large code bases, sometimes really well tested, sometimes not so much, and introducing different techniques to help, to me, make life better for developers. And that's kind of my goal, is to provide techniques and ways for developers to actually enjoy the work instead of feel like it's sort of drudge work. And so I've been doing test-driven development for, I don't know, let's call it, since the early 2000s. Uh, and test-driven development is one of those things where I feel like you either hate it because your code base doesn't allow you to do test-driven development, um, or you hate it because you've never actually learned it in a way that allows you to really understand what it's all about. Um, and I think a lot of that is because most of the time people see intro to TDD videos, it's all, you know, day one greenfield kinds of things, which is, certainly useful. And as a trainer and as somebody who studies how people learn, you want to start out with the basics. Um, but most of the time we're working in code bases that are not so amenable uh, to making that easy. Um, and over the years, when I've been practicing it, I think practice is super important. And I think that's something, and experimenting is really how we expand how we understand the things that we do. We want to get better at something, right? We don't just say, keep doing it without thinking about how you're doing. You have to do it, and you have to do what's called deliberate practice. Um, and TDD, test-driven development, to me has sort of multiple levels, right? There's a lot of nuance, and this is why I do so much of the training actually in a working ensemble where we're actually working on code and getting constant feedback on not just from the code itself, but also from me guiding us to different things. And over the years, I noticed um, I noticed something, and so that's where this idea of predictive came out. And so I'll talk a little bit about the process, and then I'll talk about and run through a little bit of the game. So, so if you're have at all read anything, if you've ever heard of TDD, if you've ever searched for it, if you've ever been exposed to it, you've probably seen something like this diagram, something where, we've got the TDD cycle, Red-Green-Refactor, as it's sometimes referred to, or even RGR for short. Um, we love acronyms, right? And so we often think, we start at the top, we write a failing test, we write just enough code to make it pass, and then we refactor to make ourselves better for the
Thank
future.
you. Yep, I guess
And
that's a different discussion. Yeah. Part of, I don't know what their strategy is for the. Makes sense. Less is
hello,
more.
somebody's talking.
Okay, I think I got everybody muted now.
Okay, thank you. I thought it was a question. And by the way, I'm monitoring chat. So if you've got a question, if you missed something, if you're confused by what I said, my policy is ask quickly, ask right away. If you've got a longer question, then you don't have to type it out. You can just say, hey, I have a question. But probably keep the longer questions till later. But if there's anything I'm saying that you want to know more about or you're confused about, go ahead and type into chat. I'm monitoring that. So the TDD cycle, Red-Green-Refactor, it's not that simple, right? If you've actually done it, you may not realize how much you're actually doing. So first of all, there's two parts, and I was showing the hat before, right? There's this part where we're changing behavior, right? This is as Jeepo Hill likes to say, this is the moneymaker, right? If there's no change in behavior, then okay, that's fine. But really, what we generally get paid to do is to change behavior, right? Adding features, maybe removing bugs, that's useful, that has value. Maybe expanding its ability to scale in terms of number of customers or things like that. That's where and this is also kind of the riskiest part, right? We're making changes to our code, which always means that something could go wrong. And the idea of refactoring is to keep the code malleable, to keep the code and increase the changeability of our code. And doesn't mean we do it every single time around the cycle, right? There's sort of like, we look for opportunities, and there are different levels of refactoring, and I have entire videos and stuff on depths of refactoring and different modes of refactoring. But that's the basic idea of this part is we've just written some code, and now we want to sort of make it fit better. But in reality, the change behavior part, this part, actually looks like this, right? When I mapped this out, when I was teaching it and I was mapping out the precise steps that I was leading people through, it looked something like this. I obviously am a fan of hexagons. I like hexagonal architecture. And this seems like a lot, but these are the precise steps that I do every single time I'm working in the red-green part of the cycle. And I looked at this and I thought, wouldn't it, yes, hexagons are the best hexagons. Wouldn't it be great if I could teach this order in sort of a flashcard way? So one of the great techniques for sort of learning things is you create flashcards. And I thought, well, maybe I could make it into a game. And I was mainly concerned with I wanted to teach these steps and have people do them in the right order and think about each step along the way. And I'll go into these steps in detail, but this was sort of the genesis of the game. And it took quite a while to sort of figure it out. And this is now what the game looks like. And we'll look at the game. And by the way, if you stay tuned till the end, I have a $10 off coupon, so you can buy the physical game. And so as I was developing it, it turned out that there was some really interesting aspects of it. And also one of the difficulties was figuring out how to inject some of the randomness that you need in a game and some of the, what was I trying to sort of get people to really think about. And one of those aspects was the predictive aspect. So let me go through the way I think I step through the red-green part of the cycle, and we'll see what I mean by predictive. So this is the hardest part, right? What should it do? Right, you're about to implement some new functionality. What should it do? It should be able to send an email when somebody gets money deposited in their account. Okay. Well, how do you know that it did it? Right? What would be sometimes we look at this as acceptance criteria, but we're really thinking small, right? So, literally, like, what do we expect to be able to observe in our code that what we wanted to do succeeded? And this is value, right? So we got to still first figure out what do we want it to do. The second part of how do we know it did it This to me is the key of test-driven development. If you can't observe any change in the system, then how do you know it worked? And if you can't observe any change in the system from code, then there's no way to write an assert. All tests generally need some kind of, we set things up, we set up the context, we execute some command, some action, and then we have to assert that the new state of the system or some observation about the system has changed in a way that we want. And I call these tiny validations because these really, the smaller the better, right? So one of the things about test-driven development is the smaller the steps, the easier it is to write things. And so we know the rule about TDD, you don't change production code without a failing test. And this means you might write a new test, or you might change an existing test, right? If I want to change behavior, oh, I don't want to send emails anymore, I actually want to send text messages, then that's a change in behavior. Or maybe I don't want to send it when any amount is deposited to account, but only when it exceeds a threshold. Okay, that's a change in behavior. So any change in behavior, right? We sometimes separate in our heads new stuff from change stuff, but from test-driven development, it's all the same thing. It is, I want it to do something different than it did now. So Janice mentions validated change in the system. So I'm talking about tests at very much every level. So I am a believer in majority of your tests are what I call IO-free tests. So a lot of people call, unit tests and integration tests, and people are very confused, including me, about what do you mean by integration tests? What do you mean by unit tests? And I prefer to stay out of the debate of what is a unit, because I just don't think it's a valuable thing to talk about. What I want to talk about is how easy is it to write this test? Am I actually testing real behavior as much as possible? So if you know anything about me, if you've interacted with me, if you've seen my streams, you know I am very much against mocking tools in a situation where you don't absolutely need them for like a legacy situation. So Janice, I'm using system as representing behavior in the code, not a complete deployed kind of system. So when we're writing a test, I might instantiate an object, do some action, right? So SEA, set up, execute, assert. I find that much easier than AAA because I always forget which A goes first. So I set up the object, I might just create it, I execute a command, and then I assert on perhaps that object or perhaps a collaborator object. Or perhaps I'm using test doubles, what sometimes are called mocks, and to verify that, right? So from the tiniest level, getting larger, how objects interact with each other, and then getting even larger, how do we interact with other systems or databases or UIs or APIs, things like that. And that stuff is like all the different levels of that. I've got articles about that and talk about that in terms of hexagonal architecture, which is one of my favorite architectures. But since I'm mentioning it, we're talking about testability. To me, the architecture, the way we organize our code, makes it and defines how easy it is going to be to test our code. And if you read, people talking about clean architecture and hexagonal architecture, it feels to me like 90% of the time they're missing the point, which is we're not organizing code arbitrarily or just to separate things or to substitute databases, which is honestly a rare thing, although I've done it. To me, it's much more about testability. How can I test this code? Can I test this code? Can I test this code, especially since TDD requires these steps, right? So no behavior change without a failing test, which means we've got to have the test running and failing before it passes. And if you've done any kind of TDD, you know that you want these tests to run fast. And what slows tests down? There are two things that slow tests down. One is a mocking tool, an automated mocking tool like Mockito or things like that. They slow it down. They have to do some extra work and stuff underneath that slows tests down. The other is I/O. You hit a file, you hit a database, you hit an external service, even if it's locally running on your machine, you hit a network socket. You even print stuff on the screen. That slows down your tests. And maybe it's only 10, 20, 50 milliseconds, but you multiply that by 100 tests, 1,000 tests, and that adds up. And so that's why I define my tests. I separate them, not unit integration, but basically IO free. Does it touch real IO or not? And I want most of my tests to be IO free. If I instantiate an object and execute a method against it, that's not hitting IO. Right? I like to think of it, it's just RAM and CPU. Is it running in RAM and CPU? That's what I want. If I substitute something that stands in for a database, but that's also in an object in memory, then that's also IO free. Even though some might say, well, that sounds integration-y. But since I'm not using a real database, it's IO free and therefore runs really fast. Then I have IO-based tests, which obviously are going to hit a database, perhaps locally, maybe remotely, hit a real service, maybe locally, maybe remotely, interact with some UI or client, again, sort of locally or remotely. And those are necessary. We need to make sure that if I write to the database, it works correctly. If I read from the database, it works correctly. And I still do that as TDD, but those are going to be slower, and those are the ones that I'm going to run less frequently when I'm really focusing on the core meaning. What is this? Why are we writing code at all? The core part of it is important, and I want to test as much of that as possible quickly with IO free tests. So we want a test to run, we want it to fail before passing. And there are a couple of different ways a test fails. In fact, there's almost an infinite way a test fails, but I'll categorize them into two. One is, and this only applies in languages that actually have a compiler, although if you're using a linter for a JavaScript or something like that, or TypeScript has a compiler, as it were, that's a place where it fails. So fails to compile is a way of failing. Here, it's pretty obvious, right? You know, often, especially, I use IntelliJ IDEA for Java. It's going to show you immediately you're trying to use a method that doesn't exist, or you're trying to use a method that has a parameter that it currently doesn't support. Oh, I want to be able to add in another parameter, right? That's the behavior that I'm changing, and now I need to do that, but it doesn't currently do that. Compile error. And so our job here at this point is I need to get out of not being able to compile. To me, not being able to compile is the worst situation to be in, because if things don't compile, I'm sure if we've all experienced, if you've done anything with compiled languages and making changes, you make a change and all of a sudden you get, 10 compile errors. And you go, okay, you fix those 10, and now there's 50 more. Okay, you fix those 50. And now there's 25. It's sort of like you don't know when it ends until it actually all compiles. And to me, that's a really bad situation to be in. And so what we want to do here is get to compiling as soon as possible so that we can actually run the test. And this is the key. Not only must the test fail, but it has to fail for the right reason. At this point, a test can fail for all sorts of reasons, but it has to fail for the right one. Well, what is the right reason? Well, if you don't know why it should fail, then you need to back up and say, what are we trying to do? So let's say one of the projects I work on a lot is a blackjack game. So let's say we want to deal a card to a player. Okay, well, currently when we say deal card, it does nothing. And so we want, when we deal a card to a player, the player now has a card. Well, what are the ways that can fail? Well, the way we want it to fail, right, before we implement that feature is we ask the player how many cards you have, and they say none. Perfect. But what if it fails because you had some code that unintentionally pre-filled some player cards? Right? Maybe it was code you weren't aware of. Maybe it was a sequence of events. Maybe it was test data that somehow got into your system. And instead of failing with 0 cards, it fails with 2. Now you're puzzled. But that's good, right? Being puzzled means that you have discovered something. You've discovered that the system is not what you expected. And so in order to not fool yourself, right? So we are very, very good at fooling ourselves. Oh yeah, I knew that would happen, right? Oh, I knew it would fail for that reason. And so what we do to protect ourselves from this kind of cognitive bias is we predict. So we predict not just that the test will fail, right? Not just saying the test is going to be red, but we say it's going to be red because we're going to expect one. That's eventually what we want, the player hand to have one card, but we expect the current behavior to say it has 0. So we're very explicit. Player has 0, we expect 1, and that's why the test fails. If it fails for any other reason, maybe you got a null pointer exception from someplace you didn't expect. Maybe you get, as I said before, maybe something else as part of the process of initialization was automatically dealing 2 cards to the player, and the behavior you're working on, you didn't realize that. And so what this does is if it does not fail in the predicted way, that's valuable information, because the last thing you want to do is add more code or change code to an existing system that presumably was working, right? All your tests passed before you started on this, right? Yeah, right? They were all passing, they're all green before you start the next red. But if it fails for an unexpected reason, that means you're missing something in your understanding about the existing system. Somewhere you have misunderstood something. You have made the wrong assumption. And better to find out now than after writing code, right? And I don't know if you've experienced this, anyone, but I certainly have, where it's like, okay, I wrote the code. It was 1 line of code. It should absolutely 100% work and the test still fails. Because you assume, and this happens to me because I'm not perfect. I do prediction, but sometimes I will forget to predict, or I will ignore the error message, and I don't read it carefully enough. And then I go write my code, and it's like 1 line of code. This is a very simple step. And it still fails. And not in the code that I just wrote, but somewhere else. And now I'm just puzzled. And so now you have 2 problems. One is your misunderstanding of the current way the system works, of how the code base operates. And 2, you've just written code without understanding how the system works and how the code operates. And so now you've got to back off your code and say, wait, what was going on? Why? What did I misunderstand? And I think this is a really underestimated and underutilized part of TDD is every time we write code, we're making assumptions, right? We cannot possibly fit the entire level of detail of the code in our heads. It just doesn't work. Our brains don't work that way. This is why we have abstractions. This is why we split things in boundaries. This is why we have objects or whatever to make the smaller things so we can juggle things around without having to know the precise details of all 2 million lines of code. And so therefore, we will never have a perfect understanding of the system. So Anita brings up the point of, couldn't this also pass because we didn't understand the code is correct? Absolutely, right? So remember, what we're predicting is not just that it fails, but fails for the right reason. So if it passes, that's also bad, because wait a second, did this, I mean, I know I've experienced this where it's like, this magically worked. Now there's situations where you're expanding tests and it covers something that the code was general enough. That's different. Here we're saying like, and that's where like I expect it to pass, and this is just a confirmation test or a backfilling of a test. But if I expect it to fail and it passes, again, that's not good. And this is why it's kind of funny where we think about green being good and red being bad. It's not that simple, right? Red could be good. If it failed exactly the way I wanted it to, the way I expected, that's good. That means, okay, at least this part of what I'm doing, I understand how the system got here, how the code got here, and what my change, my test basically is saying. And if it passes, I'm like, what am I missing? And if it fails differently, I'm like, why is that failing differently? And that will force you, well, nothing forces you, but it will guide you to go and look at the code and say, how did it get that way? What's going on? Why am I getting this thing copied 9 times? I only expected 1 copy. Why am I getting 9 copies? What's going on here? Right? And you want to do that, right? You want to say, I don't understand the system, or I'm missing something. You want that to happen before you write any more code to make the thing worse. Helen asked about the slides. Yes, absolutely. I'll be making the slides available. And of course, the recording will be available. So if everything goes well, we predict. And so what I like to do, right, again, we're really good at fooling ourselves. It's like, oh yeah, that's what I meant, right? So you predict in your head without, and you say, run the test and it fails. Oh yeah, I expected that. No, what I want you to try out. So next time you're trying out, you're practicing, you're with a small group and you're doing some learning, predict out loud. Say it out loud, because it has to become crystal clear to be able to say it out loud. Whereas in our head, our brains are happy to make it appear like you know what you want precisely. And then you try to say it and it's like, oh, that wasn't as precise as I thought. Right? So again, you want to predict precisely and do it out loud, as long as you're not going to bug anybody. Say, this test is going to fail because the player's hand is going to have 0 cards, and my test is going to say it expects to have 1. And that's why it's going to fail. And if it fails for any other reason, you got some thinking and looking to do. On the other hand, if it fails exactly as expected, that is confirmation that you have an understanding, at least of this part of the system, and that your test also works. So in addition to reinforcing your understanding of the system, it also helps you that the test is written correctly. If you didn't do the setup correctly, and the test fails because you didn't do the setup correctly, but it fails in the wrong way, then you can go, look, oh, I forgot to initialize this thing and do this other thing. So, a lot of folks say, well, how do I know the tests that I'm writing are correct, right? Who tests the tests, right? And so this is one way that this can help, right? Predict precisely, and then run the test and expect whether it's going to pass or not. And if it's not going to pass, precisely, right? Literally precisely, like predict what that error message is going to say. And it's not always easy, which is kind of amazing. Like, what are we doing, let alone writing code where we don't understand exactly how the system is going to respond to this method call? We don't understand that precisely. And right, I used to do this, and I used to train people who did this. You'd go into the code base, not TDD, and you'd make some changes without really fully 100% being clear about things. Because usually it works, but not all the time. Yes, and it helps if you're in a mob programming situation to say it out loud. And in fact, this is what I do in my learning ensembles and in my other training ensembles is, I'm not going to run this test. You cannot run the test until you've said out loud exactly how it's going to fail. Then we go run the test, and then we see what happens. So once the test passes as predicted, then it's a matter of writing the least effort code. The less code we can write here, if something does go wrong, the less code we have to look at. And so there's this additional principle of what's the least effort code we can write here. And over the years, one of the things that I found, especially after rereading Kent's book, is about this part. I used to be very careful and very cognizant and very, very concerned about writing elegant, good, clean, well-structured code right off the bat. I admit I'm a perfectionist. And so I worry about things and spend a lot of time, but write good, clean, clear code. That's a hard habit to break. And TDD really emphasizes spending almost no effort at this step. This is what we want. We want it to be able to, like, I don't care if I copy and paste, right? And so sometimes we'll return a hard-coded value. That's easy. I know that'll get me to the next step. And whenever whenever I used to see demos of that, oh, you're returning false? Come on, really? We know that's going to be a Boolean variable that you're going to have to store. Until I was, doing it and practicing it, and return false didn't make the test pass as I thought it should. I'm like, huh. Even the most trivial code still didn't make it pass. once again, I'm missing something. I need to go dive into the code and see what I'm missing. If I had written the full out code that was doing some complex decision making, it still wouldn't have worked. But now I'd have two problems. Is it me or is it the code? Is it the code I just wrote, which is, is now 8 lines of code, 10 lines of code, maybe 20 lines of code? Or is it the code that's already there? But if I write 1 line of code and it's returning a constant and it still doesn't work, well, it can't be return false. It must be somewhere else. And so this was another breakthrough for me of just slam in the code, cheat if you have to by returning, I always say lie, cheat, or steal, right? Just return a hard code value. Doesn't matter if it's correct. Is it what the test is asking for? Steal code, copy and paste, and basically give up any idea of trying to make this code at this step perfect. The reason why is we have an entire step. We have an entire step, refactor, dedicated to making the code nice and clean and well organized. And trying to do both at the same time is a lot of mental effort. And so that's why I say least effort. What is the most trivial thing you could do? The easiest thing you can do, even if it's ugly, just do it. So you write the least amount of code to get it to pass, and least effort is the way I think about it. It might be 10 lines of code that you copied and pasted from somewhere, but that wasn't a lot of effort. You just copied and pasted it. Predict now that it's going to pass, run the test, and if it passes, then you're good. And then you can go on to the next step, which is refactoring. And you can spend all the time in the world that you have, which often is not enough, but you can spend the time here saying, all right, I've copied and pasted this thing 3 times. Let me abstract this. What's a good abstraction here? Oh, I see some similarities. Let me make them more similar. All the things we do to refactor and get the code back into shape, ready for another round. So that's a lot, right? There's a lot going on here when we're doing TD. It's not just Red-Green-Refactor, right? It is all these steps, right? Thinking about what it should do. If you don't understand what it should do in a precise enough way that you can write a test, you need to do some more work. How do you know it does it? If you can't observe any change, whether it's at the object level, it changes state from having 0 cards for the player to having 1. If you can't observe that, then you have to take a step back and say, okay, I need to refactor my code so I can observe this. Sometimes it's doing a whole refactor, extracting a new class. It's like, I can't access this as private information, but if I extract it to a new class, now it's accessible publicly, and now I can test directly against that. Or sometimes it's like, it's communicating with the external system. I can't query that external system, at least I'd rather not during this kind of test. And so this is where we introduce test doubles, like a spy or a fake or things like that, so that we can observe what did it try to save in the database? I don't care about what's in the tables. What did it attempt to save? Or what message did it attempt to email? And then I can verify that. And once you get past that part, then you write the test. Should fail to compile. Not always though, right? If you're just adding on more complex behavior to methods that already exist and that are in the right form, then this step is straightforward. And then, right, write that least effort code to make it compile. In this case, it might just be creating a method and having that method do nothing. Now we can compile, we can run the test, but wait, hold on. Out loud, predict what you think is going to happen precisely. So predict precisely before running the test and watching it fail. If you run it and it passes, that's not good. If you run it and it fails, but for the wrong reason, that's not good. And then you need to back up. But if it fails in the predicted way, that's great. That's what we wanted. So this is sort of this olive green, even though the test failed, it failed because it failed in the way that you wanted it to, which meant you're on the right track. Yeah, did the prediction hold, as Astrid says, right? Or as we'll see in the game, it's like, did the prediction come through? Did the tests pass or fail as expected? And then we write the least amount of code, predict it passes. If it doesn't, well, it must have been the code you just wrote. And that's why this spending less time on making it nice, because you might have to throw it away. For simple stuff, yeah, but for more complex stuff, do the simplest thing, even if it's returning a hard-coded number. Later on, you'll have more tests that will guide you to what needs to be a variable, what needs to be a decision statement, what perhaps needs to be in a separate class or a different type. And then once you get the passes, then you can start working on cleaning up, tidying up, reorganizing, refactoring the code. All right, so that's the process. So let's take a look at the game. So I released the physical version of the game about a little over a year ago, and I had a digital version. And boy, let me tell you, putting a physical board game, card game into production is an interesting experience. But as you can see, this is actually a photo from a guy in the UK who has been using the game and playing it a lot. And one of the things, he's been sharing is his experience with it. And he actually had one of the digital copies and then one of the first physical copies. And so he keeps sending screenshots of various different people playing the game. What's interesting about the game is you can play it solo, right? So it's actually, you could play one to if you have time, up to 6 players. But generally 2 or 3 players is probably the sort of the good area where the game is moving fast enough, but also you have enough people to talk with. One of the things I found interesting is it's, first of all, I've played it with people who know nothing about TDD, and they said this is fun. So it's like, okay, great. So it's fun on the basis of it just being a game. But what this gentleman and others have confirmed for me is that it provides wonderful fodder for discussion. So what's the goal of the game? The goal of the game is to get to what I call commits. So the first to get to 5 commits wins. Or if you're time boxing, like we've only got an hour, the game can actually last a long time if you have 6 players. So you can say, let's play for half an hour, and whoever has the most commits wins. So let's take a look at the action card. So let's take a look at the game. So this board now should look familiar. These are the hex tiles. Right. This is the process that we've just gone through. Right. What should it do? How do you know it did it? Right. Code for test, predict, and so on, all the way around here to commit code. And you have your what I call your commit tracker and your risk tracker, and we'll take a look at that. And so there are 2 kinds of cards. There are these action cards, and we'll look at what these are. So they have different things on them. So we'll see that there are some red cards, technical risk cards, or also called tech debt cards. There's a refactor card. There's a predict card, and so on. And so the way the game goes is you start out here, and your goal is you want to go around as fast as possible, but taking into account safety. So the number of times you basically pass the commit code and get back to here, that increases your commit tracker. And so to play, you basically get dealt 5 cards, and you hold them in your hand. And there are a couple of variations. So there've been a number of suggestions on improvements or different rules that you can apply, and that's something that I've been collecting. Using the same setup, you can actually do things like more cooperative type of thing, or more sort of player versus player. So some of these red cards, you basically have to deal with yourself, but some versions you can basically give somebody else some technical risk. So the game starts with being on this thing, and to sort of simulate this idea of what should it do and how do you know it did it, taking some time to and thought process. What I do is I basically have you discard a card. So your turn, each player's turn consists of discarding or playing 3 cards. And then once your turn is over, you deal your cards back up to 5. So you have a hand, the other player has a hand, each player has a hand, but it's an open hand because it doesn't matter. With the standard version, it doesn't matter what other players have. You're basically competing to go around, but you're managing, in a sense, your own code base, your own workspace. So player 1 starts. They want to basically get from here to here, and so what they do is they discard a card. So they may have a card in their hand, and they discard it, and so it goes into a discard pile. And it doesn't matter what card, they have to pick one of the cards that they feel is not going to be useful, and you have to discard it, and then you get to move. And so the second action will now want to leave this spot. So let me discard another card. That's one I have enough of, so I'm going to discard it. So discard that, and I get to move here. So now we're at the right code for test. There are 2 exits. There is the green exit, which to exit you have to play the right code card. And not right as in correct, but right as in authoring. So this card. Or you could take some risk. Say, I don't need tests. This is code. I know what I'm doing. And you can jump right to write code for feature. But player 1 will play it safe. So player 1 plays it safe. They play their right code card, and they move to here. And their turn is up, and they discard their cards. And so something funny about TDD is like, I don't always do it. I do it probably like 95% of the time. But there's times when it's like, look, I'm literally like CRUD retrieving stuff from a database and inserting stuff into a database. And it's used by me, the administrator of this application. Nobody else uses it, and I use it rarely. I don't need a lot of tests. That's fine. Until stuff breaks, and that's like, I should have tested it. Sometimes that works out, sometimes it doesn't. And the game actually reflects that. So, so now player 1's here, their turn is over. Player 2 says, you know what? I'm gonna be a little more risky. So they discard a couple of cards to move forward. And they decide, I'm gonna skip. I'm just gonna go right ahead to write code for feature. So they discard a card, and they move directly to here. And then they have to increase their risk. So this is the risk. There's 2 kinds of risk. There's cycle risk, which you get going around once, and there's sort of this retained risk. Like if you get past here and you had some risk, that risk doesn't go away. So they just took on quite a bit of risk down here. The maximum risk you can take on going each time around the board. So they've got a risk of 3. But hey, look how far ahead they are. Woohoo. All right, so their turn is up. And so now we're back to player 1. So from here, in order to exit through the green, oops. Right, so this spot, if they want to get from here to here to get through the green, they have to predict and have the test fail as expected. So when you put a right code card down, because the player one exited, you have the option of doing a predict. So in order to find out if your tests match your prediction, you got to do a prediction. So you would play a predict card. So we'll play a predict card. And then this is where the test results cards come in. So this tries to simulate the idea of, well, not all your predictions will be true. So we have right code we predicted. So we pick a test results card, and it says, huh, what's this thing? Well, I have no less code cards in play. So this idea of if you've written less code, that makes it easier to predict. But here I've got none, and so it's unexpected. The test did not act in the way I expected, which means my prediction has failed, and therefore I have to stay put. So the predict card gets discarded, and now my turn isn't up. I only did one card, so I can say, all right, I've learned my lesson. Let me play a less code card along with it. And then now I'm gonna play a predict card. So now if they got this card, one or more less code cards in play, well, they've got one less code card in play. And so that means their prediction was successful, and they get to move on. So their turn is up. Since they predicted successfully, we discard all the cards, including the right code card. And now player two pays the price. So to exit, they play a right code card. So they happen to have one. If you don't happen to have one in your hand, you basically discard some cards and you can collect them. But I'm playing through sort of as if they had every card they needed. So they go here. Now they skip the part about writing the test first. But we haven't completely given up on writing tests. This is basically more test after. So we want to make sure that we haven't broken anything. We've just written some code, and we want to make sure we haven't broken any tests. Maybe we don't even write a new test. We're just running whatever tests we've got. So they've written code, and they say, okay, I predict. We look at our test results, and it says, hey, no matter what you predicted, it's good. So as predicted, the test ran and matched your expectation. So you get to move forward. And now you're at the commit stage. So here, if you had no risk, you're in good shape. You're going to be able to get a commit on your next play. But since this player has 3 risk down here, they need to roll a die. And they basically have to hope that they get the right die. So I'm not going to actually roll. I'm going to say they got a 2. Well, that's not sufficient. They weren't lucky enough. One of the many tests or a few tests that they had actually broke. Or maybe they just tried to manually test. Hey, let me make sure my code works, and it didn't work. So you now discard your hand. You reset your code risk back to 0 because you're basically doing a revert. You're completely reverting all the work you've done. You get to go here, but you don't get to claim a commit, and so you're now not in great shape anymore. Meanwhile, the other player will take it safe and continue through, and eventually they'll get through. Occasionally, though, you're going to run into some tech debt, code bloat. And so here, what this does is this affects your ability to predict what happens. So this code bloat, if I had a write code in play and I had a less code, the code bloat basically erases that less code. You've got so much code that even though you tried to write less code, you're still affected by it, right? You're affected by the code base that you're working in. So that's one of the red cards. Another one is the can't assert card. This one is you can't assert what you need to because the code's not structured in a way that you can access and observe what's going on. The only way to fix that is, luckily, there are refactor cards. So a refactor card can do multiple things. One is it can get rid of the can't assert by refactoring the code so you can assert. It can also reduce risk. You can say, you know what? I've got a refactor card. I've got some risk. I'm going to spend some time here doing some refactoring. And so you can play a refactor card and it would take any risk that you have down by 2 points. And so variations of the game is if you have one of these red cards in your hand, you can play it against your opponent to say, hey, look, you discovered that you can't assert. And so on their turn, they'll have to deal with that. And so as you can probably get a sense of, as you're playing this game, you could just play it at the level of a game. Have fun, enjoy it, get around, see who gets to commits, 5 commits first. But hopefully you're also discussing, hey, yeah, we've encountered that before, and boy, we played that price. Or, huh, that's interesting, that if we write less code, we get better with our predictions. And so the game, for me, especially in very much like a coaching or learning situation, helps open up the discussion. Maybe you've not done a lot of TDD and you want to sort of explore it a little bit. Maybe you've done it, but you haven't kind of been successful, and maybe you're thinking about what's the detailed part of the process. Because often when we're doing coding or TDD, we're right, we want to be kind of in that flow, in the zone. But that means we're not as aware of what's going on as we might want to be. And so it's very hard to sort of be in the flow, but also be aware, is this feel good? Is this right? Am I doing things and making decisions that are not quite great? And this kind of game can help surface those thoughts and discussions among team members. But game aside, I find that doing the predict part of test-driven development has really improved the way I do test-driven development. Writing less code is really an important part, but the prediction it's a constant reinforcement of, yep, failed as predicted, which means I get to go, woohoo, right? Because that's great, because it means my test is working and I understand the code, at least for this part. And that's a good thing. And what we need more of is more good stuff. And so you get more frequent, lots of dopamine hits, as Mike says. Little celebrations. So I talked about those. That's pretty much it. So I'll take any questions that you might have had. As I mentioned, for being here, you get a discount code. So LNL Save 10, if you go to TDD Game, so tddga.me, you'll see a page where you can buy the game, whether you're in the US, Canada, you'll go to one place. If you're in the rest of the world, you go to a different place. And if you enter the coupon or discount code LNL Save 10, you'll save $10 on the game. I've got a bunch in stock, so no worries about waiting. And I'm also, every time I go to conferences, I always bring a couple of copies with me so that we can play. And conferences or meetups are a great place. I've had other folks take their copy of the game to a meetup. And actually, it makes for a great presentation because you don't have to do much. You just play the game and then talk about it. So if you've got any questions or thoughts, let me hear them.
I really like how that gets people thinking about the risk and how it accumulates, even if it makes you feel like you got ahead just a little bit in it.
Yeah.
Any other thoughts or comments for Ted?
Yeah, I'm a very frequent watcher, spectator of Ted's Twitch streams, and most of the time I just sit there and enjoy how smoothly all the development is and how much joy it makes just to watch it. How you fiddle through everything that Springs throws before your feet, and I really enjoy seeing how it's done correctly and how much fun it is to do it like that.
Yeah, and Astrid, as a frequent watcher, you probably I don't always when I'm streaming, I'm obviously narrating when I'm doing it, and I don't always say out loud what I expect, but I really do try to, because again, saying it out loud not only helps the audience, but helps me not cheat myself, like not be able to say, "Oh, that's what I was thinking it would happen." I still find myself doing that. So this is one of those things where it's, you know, doing it more is better than not doing it at all. You won't. It's a hard habit to build. Even if you're good at TDD, building in the prediction step is really hard, because as soon as you wrote whatever code and you're ready to run the tests, you almost, at least I almost instinctively just hit Control R to run the test. Like, oh wait, first I got to predict.
I'll remind you.